Hi everybody, we're in chapter 1 of the trigonometry book and we're going to be doing section 1. So first let's look at an angle. An angle consists of two rays in a plane with a common endpoint. So of course these are the two sides of the angle and we would measure the angle here. This is the vertex, this point here. Now an angle's measure is generated by rotation around the vertex. So you've seen angles before, like in geometry. So we measure the angle here, like I said, and the ray in the initial position is called the initial side, and then the other ray is called the terminal side. Usually the initial side is going to be in the position of the positive x-axis, if you can see a coordinate system here. So here's a positive angle. Positive angles are measured counterclockwise. So even though this, I think your eye is probably drawn to this here between the shortest distance between these two rays. But if you want a positive measurement, you have to go counterclockwise. So that would be positive. We could also have a negative angle if we measure clockwise from here to here. Usually we measure angles in degrees. A full rotation all the way around the circle is 360 degrees. And of course 1/360th is 1 degree. So a degree is actually pretty small, and you can't exactly measure with your eye exactly 1 degree, but 360 degrees make the whole circle. We can classify angles by their size. An acute angle is between 0 degrees and 90 degrees. They have this sharp point here. A right angle is, perfectly square. The angle theta equals 90 degrees. An obtuse angle is between 90 and 100, and of course straight is exactly 180. And then we can talk about two angles at a time. Complementary angles are two angles that add up to 90 degrees. Supplementary angles are two angles that add up to 180 degrees. Here's our first example. For an angle measuring 40 degrees, find the measure of its complement and its supplement. So usually what I like to do is draw a diagram, and anytime you're working with problems, it helps to see what you're doing. So I hope that you'll pick up the habit of making a diagram whenever possible. So if we want complementary angles, then they're going to add up to 90 degrees, which is a right angle. And if one of them is 40, the other one has to be 90 minus 40, which is 50. And for part B, we want supplementary angles. So the two angles are going to add up to 180. This one is 40. If this is the other part of 180, then 180 minus 40 is 140. In example 2, let's find the measure of each marked angle. So we have, looks like a right angle here, where one angle equals 3x and the other angle equals 6x. Now what we do know about the total of these angles is that they have to be 90 degrees. They're complementary. So we can write an equation. 6x plus 3x equals 90 degrees. 6x plus 3x is 9x. And solving the equation, we get x equals 10. Now if x equals 10, then we can substitute the 10 degrees in here in place of the x. So for 6x, that turns out to be 6 times 10, which is 60. And for 3x, that turns out to be 3 times 10, which is 30. Here's the second part of example 2. Find the measure of each marked angle when we have a straight angle where one side is 4x and the other side is 6x. So what we know about straight angles is that they add up to 180. So 4x plus 6x is 180. That means 10x is 180, or x equals 180 over 10, which is 18. Then 4x equals 4 times 18, which is 72. And 6x equals 6 times 18, which is 108. Now let's talk about degrees, minutes, and seconds. 1 minute is 1/60th of a degree. So we could say this is the symbol for minute. It looks like an apostrophe or a single quote. So 1 minute is 1/60th of a degree, or we could say 60 minutes equals 1 degree. It's just like time. If you think of degrees as hours, then a minute relates to an hour the same way a minute relates to a degree. And a second is a 60th of a minute. Again, it's just like time. So here's the symbol for second. Looks like it looks like a quote. So 1 second equals a 60th of a minute, or 1/3600th of a degree, because there are 60 minutes in a degree and 60 seconds in a minute. So 60 times 60 is 3600. Or in other words, 60 seconds equals 1 minute. So to perform calculations with these, your calculator will do it, but let's just run through it by hand. So 51 degrees and 29 minutes plus 32 degrees and 46 minutes. It's just like time. If you were adding minutes and hours, then you would have to say 29 plus 46 gives you 75 minutes. And then the degrees, 51 plus 32 is 83 degrees. Now you can't leave it like this because the minutes are too large. You need to fix it so that the minutes are less than 1 degree. The 75 minutes is equivalent to 1 degree and 15 minutes, because 60 of these minutes make a whole degree. And then 83 plus 1 is 84. So 84 degrees and 15 minutes. Now if we look at part B, 90 degrees minus 73 degrees and 12 minutes. What I've done here is I've taken one of the degrees and split it into minutes already. So instead of working with 90 degrees, I'm working with 89 degrees and 60 minutes. That way when I subtract, I have some minutes to subtract from. So 60 minutes minus 12 minutes makes 48 minutes. And then 89 degrees minus 73 degrees makes 16 degrees. Now you can use the calculator. The button you're looking for it has got this degrees, minutes, seconds notation on it. And it works very intuitively. If you just put in your degrees and press the button, you'll see how to select the degree symbol, or and then you put in your minutes and you can see how to select the minute symbol. And let's do a conversion. We're going to be converting 34.817 degrees to degrees, minutes, and seconds notation. Now what I do is I think of this 0.817 as part of 1 degree. And I know that there are 60 minutes in 1 degree. So if I take this 0.817, this part of a degree, and multiply by 60 minutes, it tells us how many minutes we have. So it gives us 49.02 minutes. Now that means I have 49 whole minutes and 2/100ths of another minute. So I have to figure out now how many seconds are in this part of a minute. So we're going to say 60 degrees, or 60 seconds rather, per minute. So 0.02 of a minute times 60 seconds gives us 1.2 seconds. So I have 34 whole degrees, 49 whole minutes, and 1 whole second. And we're going to just drop this 0.2 seconds because what we normally do is just round to the nearest second. So the answer is 34 degrees, 49 minutes, 1 second. Now let's talk about standard position. An angle is in standard position if its vertex is at the origin and its initial side lies along the positive x-axis. So this angle happens to have a terminal side in quadrant 1, and this angle happens to have a terminal side in quadrant 2. And normally when we say an angle is in quadrant 2, what we really mean is its terminal side is in quadrant 2. Or we could say the angle terminates in quadrant 2. So it's just referring to the location of the terminal side. And here's a definition for quadrantal angles. An angle is in standard position whose terminal side lies along the x-axis or the y-axis, such as angles with measures 90 degrees, 180 degrees, 270 degrees. See, each of these are multiples of 90, so their terminal side is going to be on an axis, and we call them quadrantal angles, and we'll talk more about them later. Let's talk about coterminal angles. Two angles are coterminal if their terminal side is in the same position. For example, here you see the terminal side of this 60-degree angle, but that it shares a terminal side with this 420-degree angle. But the 420-degree angle goes all the way around the circle but stops in the same position. So we only get one terminal side here. These two angles are coterminal. And here's another example. This terminal side is the terminal side of 110 degrees, but it's also the terminal side of, if we go around twice and then stop in the same place, that's 830 degrees. Coterminal angles always differ from each other by some multiple of 360 degrees, because to make a terminal angle you have to add 360 degrees to it, or you have to subtract. You have to go around the other way. So for example 5, we're going to find the angle of least positive measure that is coterminal with 908 degrees. So now what we should do is we should start with 908, and we should subtract 360 degrees until we get something that's less than 360 degrees, and that will be the smallest positive measure. So 908 minus 360 gives us 548, minus 360 again, because see, that's too large, that's more than one whole rotation. So minus 360 again gives us 188. So if we subtract 360 again, we're going to get a negative answer. We want the smallest possible positive answer, so we found it. 188 degrees is coterminal with 908 degrees. So let's look at part B. Find the angle of least positive measure coterminal with an angle of negative 75. Now negative 75 means a clockwise measurement. If we want to find the smallest positive angle, we're going to add 360 degrees to that. So start with negative 75 and let's add 360 degrees, and that gives us a positive 285. For part C, let's find the angle of least positive measure coterminal with an angle of negative 800. So start with your negative 800 and just keep adding 360 until you get something positive. So 280 degrees. Now see, each of these answers that we got, negative 440, negative 80, 280, they're all coterminal with the original negative 800 degree angle, but this is the answer we were after because the instructions say find the smallest positive measure, and that's the first positive one we came to. To find an expression that will generate all angles coterminal with a given angle, add integer multiples of 360 degrees to the given angle. So if I want to generate all of the angles coterminal with 60 degrees, I could write 60 degrees plus n times 360, where n has to be some integer. So, for example, if I take n plus, or 60 degrees plus n times 360 degrees, if I let n equal 2, I get 60 plus 2 times 360, which is 780. If I let n equal 1, I get 420. Of course, if n equals 0, then 60 plus 0 times 360 is 60 degrees. And I can even let n be a negative integer, which generates negative angles there. So each of these is coterminal with a 60-degree angle. Now, locate the point -3, -5 on a coordinate system. Draw a ray from the origin through the given point, and find the distance r from the origin to the point. Now, we've not talked about the distance formula. You could use the distance formula here if you wanted to, but let's talk about the Pythagorean theorem just a little bit, because we're going to be using the Pythagorean theorem a lot this semester, and we'll talk about it more in depth in another lesson. But you probably remember that it's a squared plus b squared equals c squared, where c squared represents the square of the hypotenuse, or the longest side. If I draw a coordinate system and I find the point -3, -5, and we'll just say that it's there, then that's the distance that we're after from the origin to that point. Okay? Now, I can think of this as the hypotenuse of a triangle, and I can draw a vertical side and a horizontal side. And the location of the point tells me how long these sides are. The horizontal side is 3, and the vertical side is 5. Because think about it, from the origin out to here had to be -3. Now, I didn't use the negative, because the negative only tells me which direction to go, but the length of the side is actually just 3. And the length of this side from here, from the axis down to this point, is 5 units down. So, and again, I didn't use the -5 because the negative just tells me whether to go up or down, right? And I'm just using the 5 as the length of a side. Okay, now if I'm looking for this side R, or C rather, if I'm looking for this side C, then I have to say 3 squared plus 5 squared equals C squared. 3 squared is 9. 5 squared is 25. That equals C squared. So 9 plus 25 equals C squared. 9 plus 25 is 34. 34 equals C squared. That means that the square root of 34 equals C. So the distance R that we were looking for here is square root of 34. And it's pretty common for us to leave it in radical form. We very, very rarely, if ever, go to decimal form. But the other thing is, if this radical could be simplified, we would want to do that. Now this one cannot be. But if you've forgotten how to do it, don't worry, there are plenty coming up where we will have to simplify, so we'll review that later. Let's look at another similar example that does involve some radicals. Locate the point -2, 2 square root of 3 on a coordinate system. Draw a ray from the origin through the given point. Find the distance R. Okay, so I drew a point in the second quadrant, so the x-coordinate was negative and the y-coordinate was positive. It doesn't really matter how much it is. Notice I don't even have any tick marks here. But I know because it's a negative x and a positive y that it's somewhere here. So I can draw that ray. And again, I can draw the little triangle like I did before. Now the length of the horizontal side is going to be 2. And the length of the vertical side is going to be 2 square root of 3. Now, you know, you could figure out on your calculator how much that is in decimal form so you can visualize it better, but it doesn't make any difference. 2 square root of 3 is just a number. So we know that if we want to find this hypotenuse length, we're going to have to use the Pythagorean theorem. So again, it's a squared plus b squared equals c squared, where this is c. And so we can say 2 squared plus 2 square root of 3 squared equals c squared. Now 2 squared is 4. 2 square root of 3, if we square it, we have to square each part. So 2 squared is 4. Square root of 3 squared is 3. Alright, now 4 times 3 is 12, so I end up with 4 plus 12, which is 16. 16 equals c squared. That means when I do the square root of both sides, the square root of 16 is 4. So the side that we were looking for here was 4.